we were up to Tuesday, August 2nd for Math 1325, and we're going to be working on sections 5.1 and 5.2 today. .1 is giving you some skills you're going to need to do 5.2 actually, so come in here to 5.1. First, we're going to do this from a graph. So we have this parabola right here. Find open intervals where the function graph below is increasing or decreasing. This part of this is taught in algebra classes where you just travel left or right on a graph. And if you go left to right, if you were drawing this with a pencil, when is your hand moving downward, and then when is your hand moving upward? But the key is to go left to right, because otherwise some people look at this and say, well, it's going up this way, it's going up that way. So they think it's always increasing or always going up. So this is decreasing first until it gets to the vertex of the parabola, and then it increases after that. And normally, if you could answer either one in any order, you could go left or right and do the decreasing first, and then the increasing, but here it's forcing me to do the increasing answer first. So it's increasing from, type your answer in interval notation. An increasing and decreasing are only about the x values, not the y. So we're starting right here at -3 on the x-axis, that's where the vertex is located. From -3 to infinity, it's increasing. And you cannot be increasing at a single spot, so you always have parentheses here. You would never put a bracket, which we can sometimes do in interval notation. And then, and this is a simple example because the only other time it's doing anything is the rest of the time it's decreasing. So from -infinity to -3 is when it's decreasing. And this is typically taught in a college algebra class where the graph's already given. Okay, so now the graph is traveling left to right. I'm increasing first until you reach this kind of high point right there. Then it starts decreasing after that. So, and you just assume this continues forever unless they put like circles to stop it, like an open or closed circle. So it doesn't have an arrow, but I'm assuming this is going down forever. And even though it's mostly going down, it is slightly going to the left as it goes down. And if it does that forever, it would forever go down and to the left. So from -infinity all the way till you get an x value right there, which is -1. That's an increasing portion of the graph. From -infinity to -1, we're increasing. And then you always just pick up right where you left off. So from -1 to there, -1 to +1 is decreasing, but it won't let me answer that yet. And then 1 to infinity, I'm increasing again. You can do this, the same category more than once, or not at all. It doesn't have to always increase and decrease. So then when you get more than one answer, it says use a comma to separate it. So sometimes they have a union symbol in the toolbars, but here they want you to just put a comma. Then from 1 to infinity, it's increasing a second time. And it's only decreasing from -1 to +1. So it's not that you always have to have an infinity in one of these answers. -1 to 1. And this is a W shape that usually comes from an x to the 4th power type of graph. So again, they only want the increasing, and it could be never increasing, but it's decreasing first till you get to that bottom point. Then it increases all the way to this little high point here. So from here to there is the increasing. That's an x of -3 to an x of 0. From -3 to 0, it's increasing. from 0 until I get down here, it's decreasing again, but then right here at 3, from 3 to infinity, it increases again. So a second increasing portion from 3 to infinity. There's two decreasing portions from negative infinity until you get to negative 3. And then when you were at 0 all the way till 3 is another part. So if you get a graph that's continuous everywhere and it never stops or has a break in it, it's just continuous the whole time, if you put all these pieces together, you'll cover the entire graph. So you're actually going from negative 3 to negative infinity first, decreasing. Then you pick right up at negative 3 all the way to 0, you're increasing. Then you pick up at 0 till 3, you're decreasing. Then you pick up at 3 to infinity, you're increasing. So that covered the entire graph that way. Okay, now here's what's different. This will be a little more challenging. Suppose the graph below is the graph of f prime of x. They're giving me the derivative graph, the derivative of a function. Find the open intervals where x is increasing and x is decreasing. So this is kind of what we're going to do more of in section 5.2, but when the derivative is positive, the original function is increasing. When a derivative is negative, less than 0, the original function is decreasing. That's what the derivative tells us, because a derivative measures the slope of a tangent line at any one spot. So if you have an original graph that decreases until you get to x equals 0, and then it increases forever after that, any tangent line over here is going to have a negative slope because the graph is decreasing, it's going down. In any spot on the left side of this, there's going to be a negative slope of the tangent line, and that's what makes the derivative negative. And then any spot on the right side where the graph's increasing, you can see tangent lines would have positive slopes. So anytime the derivative is positive, the graph has to be increasing. Anytime the derivative is negative, the graph has to be decreasing. If the derivative equals 0 exactly, then you have a horizontal tangent line. And then you're not increasing or decreasing, you're just constant. And that can be at one spot, or it could be even a range of spots. So this is the derivative function. You don't want to be thinking about increasing and decreasing on this graph. It doesn't mean anything. So I'm not increasing from here till there. These are slopes of tangent lines on the original graph. So this graph is about when is it above the x-axis and when it's below the x-axis. So if you put a dot right there at that negative 3, exactly on the x-axis, if the derivative function crosses or touches an x-axis, that's a spot where the original function has a horizontal tangent line. When the derivative is exactly 0, here and here, those two spots are going to be flat spots on a graph. When the portion of the graph is entirely below the x-axis, from this arrow to that spot, that whole portion of the graph is below the x-axis. That makes the derivative negative. So I have a negative derivative all the way till here. That's a decreasing portion of the original graph. The original graph may be up here, and it would be decreasing all the way till you got to an x of negative 3. Whether or not you actually got to the x-axis there or not doesn't matter. So we are decreasing in any of these portions that are below the x-axis, and then we're increasing any portion that's above the x-axis. So the increasing only takes place from negative 3 till negative 1. And then there's two decreasing sections from negative infinity till negative 3. And from negative 1 to infinity. So again, you have to look carefully. Are they giving you the original graph or are they giving you the derivative graph? This is the derivative graph. So if I want increasing and decreasing, all I care about is what portion of the graph is above and below the x-axis. This portion here seems to be decreasing, but that's actually the original function increasing, because from right here, this entire portion of the graph is above the x-axis. So I'm going to be increasing from negative infinity until I get to negative 5, since all of that's above the x-axis. And this is a derivative graph, not an original graph. And then this entire curved part till you touch the x-axis again, that's all below the x-axis. So there's a decreasing portion of the original graph. Then there's this little curve right there where it's increasing again, because this is entirely above the x-axis. From negative 1 to positive 1, it's above the x-axis on the derivative graph, so then that's a portion of the regular graph that's increasing. And then again, you're below the x-axis from here to here. And then starting at 5 to infinity, you're above the x-axis again, so there's a third section that's increasing on the original graph. And then these two curved parts below the x-axis, there's two decreasing sections. From negative 5 till negative 1. And from 1 to 5. Whoops, I didn't take that. Negative 5 to negative 1, and then also from 1 to 5. So that's the point of questions 4 and 5. Okay, now we get away from graphs, and this is the point here, is they can give you a function that's so complicated that you wouldn't even know what the graph looks like. So the techniques we're about to learn is, how do I find increasing and decreasing sections of an original graph from an equation if I don't even know what the graph looks like? Or even if I do know what it looks like, could I use algebraic and calculus techniques to find them without having to rely on a graph? So we have an original function here, and it is a polynomial. It's a quadratic polynomial. Since the x squared has a negative 1.6, this is an upside down parabola. So if you do happen to know some knowledge about the graph, you could use that to realize what's going to happen in the answers here. It's going to increase first, reach a high point, and then go back down again. So that high point of a parabola, the vertex, that's where this is changing from increasing to decreasing. So if we do this without a graph, the first thing to do is to find what they call the critical number of numbers. Critical numbers are anything that makes the derivative 0 or undefined, as long as it doesn't also make the original function 0 or undefined. So on number 6, we write down the original f of x. Notice that's f of x, not the derivative yet. 2.7 plus 4.2x minus 1.6x squared. Okay, so first thing you have to do is find the derivative of that. And this is what we did last chapter. Any of the rules from last chapter could come up. Power rule, product rule, quotient rule, chain rule, any logs, exponentials. So this is easier because this is just a polynomial, and I can just go term by term. It's really, they also call this the adding and subtracting rule because you're adding and subtracting different parts. The power rule can also be called the constant times a power rule, if there's a constant there. So I have a constant first. The derivative of a constant is 0. I've got a linear part next. The derivative of a linear part is just its slope in front of the x. And then really the only time I have to do the power rule is right there. 2 times negative 1.6 is negative 3.2 x to the first power. Decrease the exponent by 1. Here's the derivative function. Once you get your derivative function, first set it equal to 0. Find all the zeros of it. That's why in college algebra they have a whole chapter devoted to finding zeros of functions. So subtract 4.2. Negative 3.2x equals negative 4.2. Divide by negative 3.2. So 2 negatives equal a positive. This is the same thing as 42 over 32. You can move the decimal over on each one. One place to the right on each one. And then those divide by 2, so 21 over 16. And usually they're going to want simplified fractions and not decimals. We could check if they say here, type in integer or simplified fraction. Okay, so 21 over 16 is the only number that makes the derivative equal 0. And because the function and the derivative are polynomials, polynomials are never undefined. So technically a critical number is anything that makes the derivative 0 or undefined, but often it just comes down to the 0 because a lot of the functions we get are never undefined. What would make them undefined is if there was a denominator that could equal 0 or a square root that could be negative. So most of the time it's just what makes the derivative 0, and it can be one number or multiple numbers, just depends how many times that can be set equal to 0. Okay, so the good thing about a critical number is it gives you the list of only possible chances to change from increasing to decreasing or the other way around. And if there's only one critical number, then this can only happen once. And if you know, like I said before, how a parabola looks, that makes sense that it only changes directions once. So you put any and all critical numbers on a number line, and then I only have one here, and then you just have to pick one number in each region. So I need any number bigger than 21 over 16. 21 over 16 is a little more than 1, so I would pick 2. And you could pick 3, you could pick 4, you could pick 1.9, you could pick a million. It does, any of them will give you the same answer, so you just pick the most convenient number possible. Anything less than this, 1 is less than this, but I always use 0 when I can, so 0 would be better. So we want to plug these into the derivative function. We want to know what's happening to the derivative at these spots. So I need to do f prime of 0 and f prime of 2. F prime of 0 is easy because if you plug a 0 in right there, this whole term disappears. And the answer is right there, 4.2. This answer is positive. When a derivative is positive, the original function is increasing. So you're increasing all the way till you get to that critical number in the original graph, not the derivative graph. But you plug it into the derivative to tell what it's doing. Now plug 2 in right here. 2 times negative 3.2, or I could just do 2 times 3.2 is 6.4. And then I could do 4.2 minus 6.4. So f prime, oops, I typed that wrong, 4.2 minus 6.4. F prime of 2 is negative 2.2. And it's okay if these are decimals because they never asked for these answers. So now it's less than 0, it's negative, and that means the original function is decreasing. So from the critical number and ever after, it's decreasing. And it will keep doing that forever because it can only change directions at critical numbers. That's why they're so critical. By knowing them all, you have your only chances to change directions. If there's only one critical number, the most you can do is change directions once. So I'm increasing first, and then I got that one flat spot, and then I decrease after that. The one flat spot where the horizontal tangent line would occur is at the critical number. Now, just because you find a critical number doesn't mean that it does change directions. It can increase before the critical number and increase after it. So it's not a guarantee you're always going to change directions, but it's the only chance to do so. So that's why they help so much, as it narrows down our search for these spots. And like I said, if you knew that a negative x squared graph is an upside down parabola in wherever the vertex happens to be, that's hard to tell right away, but it clearly increases first till you get to the vertex, and then it decreases after that. So this confirms what I know from a graph. But the point of these is to try to do them without graphs, or they'll give you problems that are too hard to graph anyway, just to make sure you don't graph them. But if you do happen to know what the graph looks like, it doesn't hurt to know that on the side of these things. Okay, so we increase from, it increases first, so it increases from negative infinity until you get to the critical number. So you don't have to think about the other number of the interval notation too much. It's the critical number no matter what. Critical numbers are the only ones that can go into these increasing and decreasings. And then it decreases from the critical number all the way to infinity. Okay, here's an x to the third graph. 2/3 x to the third minus 2x squared minus 126x minus 12. Long polynomial. Polynomials are continuous everywhere. They have no issues in their domain. Their domain is negative infinity to infinity. They're never undefined. So all I have to do is search for what makes the derivative 0, which I can't do until I take the derivative first. So 2/3 x to the third minus 2x squared. Sorry, I thought it was going to be plus. Minus 2x squared minus 126x minus 12. So always do the derivative first. This whole chapter is called What Do Derivatives Tell Us? So we're going to always be taking derivatives. They did this on purpose. If you do 3 times 2/3, the 3's will cancel. So the product of the exponent with the constant is just 2. You multiply the exponent to the constant. The base stays the same, and then you decrease the exponent by 1. 3 minus 1 is 2. 2 times 2 is 4. X, decrease the exponent by 1 to a 1. And the derivative of negative 126x is literally negative 126. The derivative of a constant is 0. Set this equal to 0 and find what makes it 0 because it's squared in the derivative. The derivative is always 1 exponent less than the original if you get polynomials. That means I can have 2 critical numbers. I can have a maximum of 2 critical numbers. We could also divide everything by 2 to make these numbers smaller because we have it set equal to 0. So I'm left with x squared minus 2x minus 63. Because half of 12 is 6 and half of 6 is 3. The most common way to multiply 63 is 9 times 7. So that's what I would start with first, is 9 and 7. If the last sign in a trinomial is negative, you get 1 positive and 1 negative. So we're trying to multiply to negative 63. And if this is a minus, then you're trying to subtract to the middle value. So I need to subtract the negative 2. That means the bigger number is negative, negative 9 and positive 7. 7 minus 9 is negative 2. 7 times negative 9 is negative 63. So I have 2 critical numbers, x equals positive 9 and x equals negative 7. So there's a chance this thing could change directions twice. In fact, if you know from college algebra that x cubed graphs typically go like this, see how it could increase first and then decrease and then increase, or maybe it comes down and goes like this and does both oppositely. But there's also the x cubed parent function from college algebra. X cubed without any other numbers in it, it does this. Oops, I drew that bad. Sorry, right there. This thing is increasing, increasing, increasing. It's flat for just that one moment in time at 0, and then it increases afterwards. So this one does not change directions even though it's an x to the third. This one is always increasing, or at least it's never decreasing. So it's not a guarantee that you're always going to change directions every time you get to a critical number. So that's why I have to make a number line, put the smaller number on the left, bigger number on the right, 7, negative 7, and 9. Plug in one number from each region. I would definitely pick 10 for bigger than 9. I always pick 0 when I can, if one of these is not a 0 already. And then something less than negative 7, so I'll just pick negative 8. And here's where, if you have a graphing calculator, you can speed things up. Here's my original derivative function, although it turns out you can plug it into the reduced one too. But in a graphing calculator, I can type, I want to type 2x squared minus 4x minus 126, and first I'm going to plug in negative 8. So 2 parenthesis negative 8 parenthesis squared. I'll show it to you closer after I do it all. Minus 4 parenthesis negative 8 minus 126. So the important part of these is getting these calculations to see if they're positive or negative. We don't really care what the answer is, just is it positive or negative. So I plug negative 8 into the derivative function, and the answer is positive 34. So I know this portion of the graph has a positive derivative. Therefore, it's an increasing portion of the graph on the original function. The derivative is positive. That tells us the original's increasing. So it is probably doing like a typical x to the third graph and increasing first. I don't have to waste time finding f prime of 0 because putting zeros in for these x's will make them disappear. F prime of 0 is right there, negative 126. It's definitely, that's why I like to plug 0 and you don't even have to calculate it. That's definitely negative, then you are decreasing. That's this little portion of the graph right there. So now I need to plug in 10. Here's a shortcut in these graphing calculators. If I press second and the enter button, it calls up the last statement I typed in, and then I can use the arrow keys and back up on top of those negative 8s and just type over them with a 10 if I want to do f prime of 10 next. 10. So now I've got it with 10s there. That's also 34. Sometimes that happens where, since I went one unit this way and one unit that way, the answers sometimes are the same. Not always, but sometimes. But the more important thing is that I got a positive, so that I'm increasing again. Now, be real careful about this. It's easy to, when you get to the answers, people will, I do it too sometimes, you accidentally put answers down for these numbers you were working with because they're still on your mind. When you're done with a checkpoint, cross it out because it's never going to be part of an answer. The only answers you ever put in are critical numbers and infinities. So I would only put in a negative 7 and or a 9 or some kind of infinity to these answers. So we're increasing from negative infinity until I get to negative 7. Then I decrease right there at negative 7 till 9. And then I increase again from 9 to infinity. But the homework will probably want this and this with a comma between them first, and then they'll let me put this one in. Oh no, first they want the critical numbers. So negative 7 and 9, we got 2 of them. It's increasing from negative infinity until the first critical number, which was negative 7. And then it also increased from the second critical number, 9, all the way to infinity. And it was decreasing in between the two critical numbers from negative 7 to 9. Okay, so what if we did a cubic one already, so I'll skip this one. Here's a fourth power. So 8's just like 7, just different numbers. It's another cubic. You're going to end up with possibly 2 critical numbers and 3 sections of check, and maybe this will happen again, or maybe it'll be increasing, increasing, decreasing. Or maybe it could stay the same. You don't just assume that it's always going to be changing from section to section. F of x is x to the 4th plus 16x to the 3rd plus 40x squared plus 9. Always get the derivative first so you can find your critical numbers. So the derivative of x to the 4th, power rule, 4x to the 3rd. And really the chain rule applies, but the derivative of x is just 1, so that's when it really doesn't apply. And then I've got 3 times 16, 48, x to the 2nd, and then 80x, and there was no x term. It jumped from square all the way to just 9, so the derivative of 9 is nothing. Set this equal to 0. It's never undefined because it's a polynomial. All of these numbers divide by 4, so if you can do that, that definitely helps. You can't always do that, but it helps when you can. So I'm left with x to the 3rd plus 12x squared plus 20x. And all of those have a GCF of x, so I can pull x out. X squared plus 12x plus 20. We need 2 numbers that multiply to 20 and add up to 12. And if the last sign's positive, they're both whatever the first sign is. So they're definitely both positive. 5 and 4, maybe you're thinking, but 5 plus 4 doesn't add up to 12. 10 and 2. Oops. 10 times 2 is 20, and 10 plus 2 is 12. So because the derivative is 3rd power, I could have 3 critical numbers, and I got 3 unique ones. 0 itself, -10, and -2. Here are my only 3 spots I could possibly change directions in the original function. 0, -10, and -2. I don't think it matters what order you type those in. You just want to get all 3 of them. But it does matter the order of them when you put them on a number line, though. So I'm going to put -10 first, then -2, and then 0. Since 0 is one of my critical numbers, I can't use that as a checkpoint. So I'm going to do 1 and -1. Those are good around 0. -3 would be the smallest value I could get past -2, and I would just do -11. We need f prime of -11, f prime of -3, f prime of -1, and f prime of +1. And this is where it can take a while if you have to plug and chug away at this. And it'll be the same whether I plug it into the complicated one or the simpler one. So I'm just going to use the simpler version. And if I do -11 first, it'll be parenthesis -11 parenthesis to the 3rd power. For right, I'm plugging -11 in right there. Plus 12, then -11 squared. Plus 12, -11 squared. Plus 20x, so plus 20 times -11. So there I am plugging -11 into the derivative function, a simplified version of the derivative. That's -99, and we don't really care about the value -99, but it's negative. This is what's happening in the derivative. So that tells me in the original function, the graph has to be decreasing from -infinity till you get to -10. So now I want to change the -11s to -3s. If I press second enter, it calls it up. Now, if you were changing negative 11 to say negative 14, you could just type over the second one, but since I need a negative 3 and there's 2 slots, you can hit 3 and then hit delete, D-E-L, delete. Delete that second one. 3 delete and 3 delete. That's quicker than retyping the whole thing. Now it's switched to positive 21. So now the derivative is positive for any value between negative 2 and negative 10. So that means the graph is always increasing between those two. And you literally cannot change from increasing to decreasing unless you do so at a critical number. So I don't need to check negative 4, negative 5, negative 6, whatever negative 3 is doing, they're all doing the same thing. So then negative 1, now I can hit second enter and just change all the negative 3s to negative 1s by typing over them with a 1. Negative 9. So you'll see this with polynomials, they will tend to switch back and forth in each section. So now we're back to decreasing. And then finally, if I hit second enter, I can just delete the negative 1, the negative off the negative 1s. Delete the negative. Delete the negative. Delete the negative. Positive 33. Another increasing. Because they want increasing answers first always, find this portion here, cross out your checkpoints because they're not going to be part of the answer no matter what. So I'm increasing from negative 10 to negative 2 and from 0 forever after. And that means I'm decreasing in the other two sections from negative infinity till negative 10 is when it's decreasing. And then again, between these two critical numbers, negative 2 and 0, it's decreasing. And literally, this takes you from all four of these from negative infinity to infinity. You go from negative infinity to 10, negative 10, then you pick up at negative 10 and go to negative 2, then you pick up at negative 2 and go to 0, then you pick up at 0 and go to infinity. And that's because a polynomial is continuous everywhere. So I'm increasing from negative 10 to negative 2. And from 0 to infinity. Yeah, 0 to infinity, if I remember that right. And then I'm decreasing from negative infinity to negative 10. And between negative 2 and 0. These x to the fourth original graphs look like a W shape, so that's why it does that. They often do anyway. Okay, so what if you have a square root? Let's see, this is number 10. So you have an original function that's a square root. That's not continuous everywhere. So I would rewrite this as x squared plus 2 to the 1/2 power. So the derivative of that is, using the chain rule here, we would do the outside portion first, 1/2, write down the inside stuff, decrease the exponent by 1, and then chain on the derivative of the inside. The derivative of x squared is 2x. And the derivative of 2 is nothing. So this 2 can cancel that 2. The x would stay in the top of the fraction. And I could put this in the bottom to make it a positive 1/2 and even put it back as a square root. So once you have radicals and denominators, now all of a sudden you can get undefined answers. But luckily for this one, x squared plus 2 is never undefined inside of a radical, because anything squared is 0 or higher. And if you add 2, this is always 2 or higher. So there's no way this radical could be the square root of a negative, but if it could, then I would want to exclude those spots. And then it can't even equal 0 either, because the lowest it'll ever be is 2. So x squared plus 2 equals 0. You technically should set that to 0 to see what makes the bottom 0. If the bottom is 0 in a fraction, then it's undefined there. And critical numbers can be from undefined values of the derivative, as long as it doesn't make the original undefined. So a fraction is 0. Let me say it this way. A fraction is 0 when the top is 0, and a fraction is undefined when the bottom is 0. So if I was looking for critical numbers, and if my derivative is a fraction, you should set both the top and the bottom separately equal to 0. Anything that makes the top 0 makes the whole derivative 0. Anything that makes the bottom 0 makes the whole derivative undefined, and all of any x values for all of that are critical numbers, unless the undefined ones also make the original undefined, which happens sometimes. But this can never be 0. So the bottom can never be 0. This derivative can never be undefined. It's defined everywhere. I have one critical number, only 0. So I just need to do a -1 and a +1 into the derivative function and plug it into here because nothing really reduced. So f prime, let me do the easier one first. F prime of 1, you'll get a 1 in the top. And in the bottom, 1 squared is 1, plus 2 is 3 squared, 1 over the square root of 3. I don't care what that equals. I don't care if in other classes, they might have you rationalize a denominator. It doesn't matter here. All that we care about is that positive or negative? It's clearly positive. The derivative is positive for any positive value that you plug in. Therefore, the original graph is increasing forever after 0. And if I do f prime of -1, oops, I wrote that wrong. F prime of -1, the top would be -1, but the bottom would be the same thing because -1 squared is +1, plus 2 is 3. So you get the same thing, but it's negative. Now, there was a potential, if there wasn't a square here, there was a potential in some scenarios where you could get negative divided by negative, and then this side could be positive too. It could be positive, and then it would never change directions. But I did get a negative. So the graph is decreasing first, and then it's increasing second, and you probably don't even know what this graph looks like, and only at 0 does it change directions. So that's as good as I don't have to know what this graph looks like to answer this. We're going to be increasing from 0 to infinity, and we're going to be decreasing from -infinity to 0. And 0 is the only critical number. We're increasing from 0 to infinity. And we're decreasing from -infinity to 0. Okay, so here's another power rule would apply to that one. This is a chain rule. Here's a product rule that even involves exponentials. So you'd have to do first times derivative of the second, and the second times the derivative of the first, and then look for what makes that 0 or undefined. Here's just a power rule with fractional exponents. Let me do one of these business problems. Here's a good one. The projected year-end assets in a collection of trust funds in trillions of dollars, wow, that's a lot of money, where T represents the number of years since 2000, can be approximated by the following function. So 0 to 50, is my domain, although 0 means the year 2000, so 50 would mean the year 2050. They've got a funky polynomial here with messy decimals because this is a business setting with trillions of dollars. When is the function increasing? When is it decreasing? This is what a business would like to know. They want to know when their assets are increasing and when they're decreasing. So now we're limited to 0 to 50 though. So if we're going to look for all the critical numbers in this, and it's going to turn out there could be 2 of them because the original function's cubic, so the derivative function will be squared. And if any of them are not in the range 0 to 50, then any ones that fall outside of that range, we just get rid of them in this problem. So we could end up with 1 or no critical numbers because they put a limited domain on us, just to have a setting like a business problem. So that could always be possible, but I'm guessing here that probably if we get 2 critical numbers, they're probably going to both be between 0 and 50, but maybe not. So a of t, the asset function, in trillions of dollars, that's probably what the t is for. This is problem 16. 1, 2, 3, there's 4 zeros there first. 1, 2, 3, 4. 395 t to the third. Minus 006 10t squared plus 0682 t plus 4.17. That's the original function, definitely a polynomial. So the derivative, it's messy with the decimals, but not hard because it's just a power rule. So I need to do 3 times the front decimal, 0.0000395. So there's 3 zeros, then 1185. 1185. And then that'll make the exponent decrease by 1 to a square. Now it'll be minus whatever 2 times this decimal is, 2 times 00610. So negative 0122 t to the first power. And then plus this t to the 0 power. So that would be the polynomial. And so we need to set this equal to 0. Now this is messy enough that probably the only way to get these 2 answers is the quadratic formula. And this is what can happen sometimes in a calculus class. You have to do a lot of messy algebra sometimes. So there's going to be 2 possible answers, and because these are messy decimals, the critical numbers themselves might be a messy decimal. And this is perfect for the quadratic formula then. So opposite of b, plus and minus square root b squared, and if it's just technically negative, but when it's squared it's going to turn positive anyway, minus 4 times a times c all over 2a. And with graphing calculators especially, this isn't too bad to do all these messy decimals. So inside the radical, I've got a 0.0122 that's squared. Whether I do it positive or negatively, it's going to be positive. And that's a really tiny number there. But then I could hit minus 4 times 0.0001185 times 0682. So this is the inside of the radical right here. And it's so small it's put into scientific notation. But if I square root and then hit second and the negative key, that grabs the answer so I don't have to try to type it, which would be messy if you don't know what that means. But there, that's the radical part. So now I have 0.0122 plus or minus, and then this 0.10794,128. And then the bottom is 2 times 0.0001185. So let me show you this in case this happens to you. 2.37e negative 4, that means you move the decimal over 4 times. So it takes one spot to move past that 2, and then you'd have 3 zeros. So 0.00237. So I just need to do one of these as a plus and the other one as a minus. I can do it here where you'll see this better. Oh, I can't see that. Okay, how about over here? Okay, so I'm going to put in 0.0122 plus 0.010794128 equals divided by 0.00237. So this one is 97.02, but notice that's past 50. We were limited to 0 to 50, so this one's out because it's not in the 0 to 50 range. And then we need to do 0.0122 minus 0.010794128 divided by 0.00237. This one's okay, 5.9. So even though there is technically 2 critical values, there's only one in the range from 0 to 50, because that's what this problem put as a condition. So that's the only one we care about. So I can just make a number line around 5.9. It's not exactly 5.9, but for plugging numbers in, that's good enough. 5.9. I would definitely plug in 0 and 6 into this derivative function. And 0 is easy. The answer is right there. So, and I don't care the answer. I care about positive or negative. It's positive when I plug 0 in. So the graph is increasing, and it possibly could be negative infinity to this, but it's from 0 to this because we have that hard 0 to 50 limit. So we're definitely increasing from 0 to the critical number. And then if I plug 6 in, that'll take a little longer, but even here, I think you can see that. 0.0001185 times 6 squared, or I could put times 6 times 6, minus 0.122 times 6 plus 0.682. That answer is negative. So as often the case with polynomials, it does switch from one to the other into different sections. So then it's decreasing. And then it'll turn around at that 97-ish, whatever that was. It'll probably increase after that, but we don't care about that here because we have our 0 to 50 limit. So it's only increasing from 0 to the decimal 5.9. Notice it says round to the nearest tenth, so I was wondering how they were going to handle that messy decimal. So just 5.9 luckily. 0 to 5.9, it's increasing. So then that's when their assets are going up, so maybe that's when they want to do whatever their business is about and make sure they get it in those years. From the year 2000 to almost the year 2006, it's going up. And then it's going to decrease the rest of the time because it'll actually decrease all the way to 97 point something, but it's going to stop at 50 because our limit is 50 here in the domain. So these business problems, you're doing the same thing in what the beginning of the sections are about. You just have these business settings, and it often makes the problems real messy because of that. But I'm already almost an hour into this video, and we've only covered the first part of this. So let's go to 5.2 is a continuation of what you're doing here. 5.2. Okay, so now what's different here is you're still going to try to figure out when is the graph increasing and then when is it decreasing, but we're going to pay closer attention to these spots where it changes directions. If a graph changes from increasing to decreasing, which can only happen at a critical number, then that critical number is called a relative extremum. Mum singular, ma for plural. So this says find all locations and values of the relative extrema. So this graph only has one of them. It has a relative maximum right there. And the location means the x-coordinate, the value means the y-coordinate. So there is a local maximum of means the value, of 9 at the x value of 1. And we're first doing this with graphs, and then later we'll do it with derivatives. So now I have a relative minimum. A relative extrema is generic for max or min, but here it's a relative minimum. There's a relative minimum of 1, of is the y-coordinate, 1 at an x of 0. It turns out that derivatives of corner points, I think we talked about this in the last chapter, derivatives of corner points don't exist. So this would be a case where if you were solving it from the equation, the critical numbers are anything that make the derivative 0 or undefined. One example of an undefined derivative is a corner point like this. So that can still be a critical number. So even though the derivative doesn't exist there, it's a critical number where I could possibly have a change in directions, which is exactly what happened there. Okay, so now if you're traveling on the graph, you're increasing first, and then you reach this maximum spot. That's why they call it relative extrema or relative maximum, because, or it's sometimes called local too, is another way it's expressed. Local, in this little vicinity, there's a high point, but it's not necessarily the highest point of the whole graph. In fact, the graph goes up to infinity. So this is a local maximum, a relative maximum. If you think about like riding a roller coaster, you're going up, 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 you get to the highest point and then down you go. So when you change from increasing to decreasing, that's a local maximum of 3 at x equals 5. And then there's a local minimum when I get here and change directions, a local minimum of -3 at x equals 7. So I'll let you do that one. It's very similar, just going to have multiple ones. And here's the graph of the derivative again. So this is that derivative graph. This is when, if you're below the x-axis, is when the derivative is negative, and that means the graph is decreasing there. So you're decreasing all the way till you get to -2, and then you increase all the way till you get to +2. So at x equals -2, it's changing from decreasing to increasing. That's a local minimum. There's a local minimum, okay, at x equals -2. And here they don't care about the value. We would have to see the original graph or have the original function to tell that. So now they just care about the locations of them and not the values of them. So it decreases and then changes to increases. Think of drawing that out. It decreases and then it changes to increases. That's a minimum. Then from -2 to 2, the original graph is increasing that whole time because that derivative is entirely above the x-axis. So you're increasing till you get to 2, and then at 2 you switch and start decreasing because now you're below the x-axis in the derivative function. So you're changing from increasing to decreasing. That's a local maximum at +2. So remember, if you have the derivative graph, you don't want to look at is this graph increasing or decreasing? You want to look, when is this graph below the x-axis, above the x-axis, below the x-axis? That tells you when it's increasing or decreasing in the other graph. So similar deal here. Okay, so now here's where we get the actual equations to work with. This is number 7. So I have my original function, x squared minus x minus 3. First you find the derivative, 2x minus 1. Set that equal to 0 or check when it's undefined, but polynomials are never undefined. So this is going to have one critical number only. Divide by 2, 1/2 is my only critical number, my only chance to have a local max or local min. Only chance to change directions. So put that on a number line, and I would pick 0 and 1 to plug into the derivative function. So if I plug 0 in right here, you'll get -1. The derivative is negative for any value less than 1/2, so the original function is decreasing any value less than 1/2. And then if you plug 1 in, 2 times 1 is 2, minus 1 is 1. The derivative is positive, anything bigger than 1/2, so the original function's increasing for anything bigger than 1/2. And then here's where I like to do this and sketch this out. If, and this is not the actual graph, but this is what's happening in each section. The graph is decreasing in some fashion all the way till that critical number. It's flat at that one moment in time, and then it's increasing forever after. So this is a local minimum. So you can either memorize that if you decrease first and increase second, that's a local minimum, or just sketch it real quick and you'll tell that's a local minimum. This is called the first derivative test. The first derivative test uses the first derivative. By plugging in critical numbers into the first derivative, or checkpoints around the critical numbers, you get to tell whether the graph's increasing or decreasing, and if it switches from decreasing to increasing or vice versa, then you get local maxes and mins. If it's decreasing or increasing on both sides of a critical number, then there is no local max or min there. And that can happen. It's just, we're doing some of the easier ones first so you learn the process. So this is a local minimum, and I don't know the value of it, of something, but I know the at x equals 1/2. At x equals 1/2, that's the location of the local minimum. To find the value of it, you have to go back to the original function. So here's where you could get confused on a test and wonder, when do I plug numbers into the derivative? When do I plug them into the original? We want the value of the local minimum, which is how high it is on the original graph. So then you have to plug that into the original function. Critical numbers always get plugged into derivatives, but if you want locations of spots on a graph, you have to plug it in the original graph. So 1/2 squared minus 1/2 minus 3. Here's another time where graphing calculators are helpful, because I can type 1/2 squared minus 1/2, and I'm just hitting 1 divided by 2 for that, minus 3, and it may be a decimal, which they sometimes won't take. But then if I hit math, enter, enter, it turns decimals into reduced fractions. So there's a local minimum of -13/4. That's the lowest the graph gets in that vicinity. I mean, it may or may not be the lowest overall. Actually, it is the lowest overall here, but whoops, in general, it may not be the lowest point in the whole entire domain of the graph. But here we have a local minimum of -13/4 at x equals 1/2. And I don't know if they want all of that, but they probably do. Yeah. So there is no relative maximum because I only had one critical number, so the most I could get is one of these. The function has a relative minimum of -13/4. I'm checking if they want decimals or fractions, but it doesn't say. So usually they like exact answers, but maybe they would take a decimal here. That was exactly negative 3.25 at x equals a half. Okay, so let's see which ones might be good to do that we haven't done yet. That might be a good one there. Let me go back to that. Number 9. What if you get a rational function? Number 9, the original function is a rational function. X squared minus 8x plus 16 over x minus 10. So first I got to find the derivative, and this is going to involve the quotient rule. So second times derivative of the first, and that's easy because it's just a polynomial. The derivative of the first would be 2x minus 8 minus the first times the derivative of the second, and that's easy because it's linear, so it's just the constant in front of 1, over the second squared. Now, in chapter 3, they let us put these answers in often, and we didn't have to waste time cleaning them up and simplifying them. But here we're going to need to do that because we need to know when this equals 0 and when this is undefined, and it will be too hard to know that from a really messy version of it. So I'm going to go ahead and clean this up and get 2x squared minus 8x minus 20x plus 80. Here's a very common algebra mistake that's often in calculus, where you have a negative in front of a parenthesis. It goes to everything inside of there. Negative x squared, positive 8x, and negative 16. And if this wasn't a 1, I would have to distribute that 1 first. All over the second squared. So 2x squared minus 1x squared is 1x squared. I get a little lucky here that the negative 8x and the positive 8x cancel, but if they didn't, I could add all the x's together. So negative 20x, and then 80 minus 16 is 64. So that's as simple as the derivative function can get. Because it's a fraction, the critical numbers are going to be anything that makes the top 0, that'll make the whole fraction 0. And anything that makes the bottom 0 will make the whole fraction undefined. And that's technically, we have to get all of those numbers that do that, because critical numbers are anything that makes the derivative 0 or undefined, as long as it doesn't make the original undefined. So the top, I could factor that. So there's going to be 2 numbers that make the top 0. The plus here at the end means you got to get 2 of these signs. There's definitely 2 negatives. Now you may be thinking 8 times 8 for 64, but 8 minus 8 is negative 16, not negative 20. But another way to make 64 is 4 and 16. And negative 4 plus negative 16 is negative 20. So the top equals 0 at 2 spots, 4 and 16. There, we got at least 2 critical numbers now. So we have a chance to have a local max and a local min, or 2 local maxes or 2 local mins at these spots. And then the bottom, if you set that equal to 0, that's what's nice about 0, is if I do things like dividing out the common factor or taking a square root, it doesn't change that side of the equation. And there's no such thing as plus or minus 0, so it's just 0. So add 10, you get another potential critical number of 10. but 10 makes the original function undefined also. So if a potential critical number makes the original function undefined, then it's not a critical number. And the main reason why is on this rational function, there's going to be a vertical asymptote at 10. And at a vertical asymptote, the graph doesn't exist there. You can't have a max or min at a spot the graph doesn't exist. So if your graph did something like this, there's no max or min at an asymptote because you never cross or touch that. So otherwise, I would have included that though. If it had been from a corner point instead of from an asymptote, then it could have been included as a critical number. Okay, so we need to take our simplified derivative function, and we got to plug these two derivative numbers in, these two critical numbers. So 4 and 16 are my only two critical numbers. I would choose 17, 5, and 0 as test points. And again, all we care about is the derivative, positive or negative. That'll tell me if the original function is increasing or decreasing. So plug 0 in, that's nice. 0 will make all these x's disappear. The top will just be 64. And the bottom will be negative 10 squared, which is positive 100. I don't care what 100 divided by 64 is. It's positive. The top's positive, the bottom's positive, so any number less than 4 is going to give me a positive derivative. So the graph is increasing first. We're increasing until we get to the value of 4. Then, because the derivative is 0 there, it's a flat portion of the graph. And then, does it decrease after that? If so, then I've got a local maximum, but it could increase again, and then there's nothing there. So now we got to plug 5 in, and this could be a little more challenging if you don't have a graphing calculator. But plug in 5 into this. The top would be 5 squared minus 20 times 5 plus 64. All I care is it positive or negative. The top is negative. The bottom would be 5 minus 10 parentheses squared. But anything squared is positive. So I don't care what negative 11 divided by 25 equals as a number. It's just a negative divided by a positive is negative. The derivative is negative anytime you're between 4 and 16. So the graph's going to be decreasing that whole time. So the first derivative test is telling me that I've got a local maximum up here because the graph changed from increasing to decreasing at a critical number. So I can already say there's a local maximum of blank at x equals 4, the critical number. Remember, don't plug in, never put check numbers into answers. And then I can't tell what this is until I do f of 4 back in the original problem. I'll wait till the end to do that. But whatever f, not f prime, but f of 4 is, that's the value of it. Now, this could decrease and keep decreasing, then I'm done, but maybe it decreases and turns around and increases, then I've got a local minimum too. So what would f prime of 17 equal? Put 17 into the top. 17 squared minus 20 times 17 plus 64. Plugging 17 in gives me a positive this time. And since the bottom is squared, anything squared is positive. Positive divided by positive is positive. I don't care what 13 divided by 49 equals, but it's positive. The derivative is going to be positive for any number bigger than 16. It's actually 0 exactly at 16, so there's a flat portion of the graph there, and then it's positive forever after. So there is a local minimum of blank at x equals 16. And then f of 16 will give me the value at that spot. So this is called the first derivative test. To do the first derivative test, you have to get to a critical number. and you need to check one number less than that, one number bigger than that. If the derivative changes in sign on each side of that number, then you have either a local max or min, depending if it's positive first or negative first. But the downside is you really have to check both sides. I have to know that this is positive and this is negative just to check for this answer. Then I reuse this one, and this is negative and this is positive, tells me that answer. But it takes two calculations at each spot to tell, even though you're kind of sharing that one in the middle. Later in this chapter, we're going to do something called the second derivative test, where you can get these same answers with one calculation instead of two. And that's when we're given a choice, we like that better, but you don't know that yet. So I need to do f of 4 and f of 16 if they want the values, and I'm checking they do. See how they say of blank. So we need the values. So unfortunately, I have to go back to the original problem and stick in 4 and 16 there. Again, now we actually need to simplify this. We don't just care if it's positive or negative. So 4 squared minus 8 times 4 plus 16. The top is 0. And clearly, the bottom should not be 0. It isn't. 4 minus 10 is not 0. So 0 divided by anything is 0. So the bottom couldn't have been 0, because then we would have had another spot possibly for a critical number. So there's a local maximum of 0 at x equals 4. In other words, the coordinate 4, 0 is on the graph. And it's a local maximum there. And then if I do f of 16, the top would be 16 squared minus 8 times 16 plus 16. The top is 144. The bottom would be 16 minus 10, or 6. 144 divided by 6 is exactly 24. So there's a local minimum, although that doesn't make sense that that's 24. I must have did something wrong, because the minimum can't be higher than the maximum. 16, 4. Let me try that one again. 4 squared minus 8 times 4 plus 16. Maybe I just typed it in wrong. Oh, it's 0. F of 4 is 0. Didn't we say local maximum first? That doesn't make sense. 16, 24. 16 squared minus 8 times 16 plus 16 divided by, oh, it's divided by 6. Okay. No, that still doesn't make sense, huh? I'm doing something wrong. Did I write the problem down right? Yeah. So we have maximum, minimum. F of 4, negative 6. Does it make sense? Huh. Well, let's just see what's wrong here. So what I got was a relative maximum of 0 at x equals 4. And a relative, well, I guess that could be true. I'm thinking of overall maxes and mins. That's possible. Maximum goes down. No, really shouldn't do that though. 24 and 16. Because it's going to keep going down until it turns around to this point. This number cannot be bigger than that number. Something's definitely wrong here. Oh, huh. It seems like that shouldn't work. Oh, I know why it's okay. Okay. It wouldn't be right if you had a polynomial, but we have a rational function, is why that's okay. So then the graph just starts over again on the other side of the asymptote. So you can have a situation where this is curving like this and going through 4, 0, and maybe it comes like this where it comes down. Well, that wouldn't be it either, but see, it's hard to know without graphing this whole thing what's going on in this graph. But in a rational function, because of the asymptote, you can have a relative maximum in some fashion like so, right at 4, 0. and the graph completely starts over on this side. So there can be a minimum here at 1624 just because they're separate graphs. In a polynomial, that would never happen. In a polynomial, if you hit a maximum, local maximum 4, 0, you're going to go down until you get to the local minimum. That's when you're turning around. So this point could never be higher than this point. But that's because a polynomial is continuous, where this is not continuous. When there's a break in the graph in some way, then this can be lower. The maximum can be lower than the minimum only because they're local maxes and mins. So what's happening in that vicinity, this is the highest point, but it doesn't mean it's the highest point overall. But also what's true is in polynomials, once you leave a local maximum, you're never going to turn around again until you pass the local minimum, if there is one. So because you have to go down to get to it, there's no way to go back up again before you go down again, unless you had another critical number there. So that's why those critical numbers are so important. Okay, so yeah, I was messing that one up. So here's one you just have to do the product rule. I just did a quotient rule example. Do the product rule for that one. Here's an easy one. Use the derivative to find the vertex of a parabola, because the derivative of this is negative 4x plus 4. The derivative of that is negative 4x plus 4. It's only going to have one critical number. It's going to have a positive 1 critical number. And then I could plug in 0 and 2 into the derivative function. 0 and 2 would be 2 good test points. This is an upside down parabola too, so it should increase first and decrease second. It does have a local maximum. And in a parabola, the local maximum or local minimum occurs at the vertex itself. So, and then if you knew that, you wouldn't even have to use derivatives. You could just use algebra knowledge to how do you find the vertex of a parabola. You do the opposite of b over 2a, and that came out to 1, and then f of 1 would tell you the y part of the vertex. 1 squared is 1, times negative 2 is negative 2, plus 2 is 0, and then 4 times 1 is 4. So the vertex of a parabola is going to be the local max or local min. In fact, it's the absolute max or absolute min of the whole graph. But so that was an easy one. Find locations. Okay, this is good to do this quick. The graph of the derivative is shown. This is the graph of the derivative. Find the locations of all relative extrema. Locations are the x values. So when the derivative is 0 are the key points on the derivative graph. Right here at 0 and right here at 4, those are when the derivative is 0. Since this is a continuous graph, it's never undefined. There's 2 critical numbers, 0 and 4. If you had the original graph, you'd want to know where is the tangent line horizontal. If this was an original graph, there would be 1 critical number right there at x equals 2. But in a derivative graph, it's where it crosses the x-axis. And then it's decreasing before that because I'm below the x-axis. It's increasing after that. If you decrease first and then increase second, you have a local minimum. So there's a local minimum exactly at x equals 0, and we can't do the value from the derivative function, so that's why they're not asking for it. And then if you increase above the x-axis is an increasing portion of the original graph, since that's when the derivative is positive, then you hit the 1 time the derivative 0 there, and then you're below the x-axis, now the derivative is negative. You just switched from a positive derivative to a negative derivative. You switched from an increasing to decreasing portion of the original graph. So at x equals 4, that's a local maximum. And we can't tell the values because we need to either see the original graph or have the original function. So that one wasn't so bad. Okay, so we're almost an hour and a half in. Let's try one of these business problems. Which one looks good? Here's one again with these messy decimals. And we've got a 0 to 24 range to go between. So first we want to find the derivative. do 3 times this decimal, and I'll ignore the negative and just put the negative in my answer, 005834. So we need a negative 017, 502, and then the t to the third will drop to t squared, plus 2 times this decimal, 2 times 1925 is 385, t to the first power, and then minus this decimal because that's linear, so the derivative is just a constant in front of it. And then the derivative of this is nothing. Okay, find any relative extrema, maxes or mins. This is a quadratic derivative, so that means it could be equal to 0 twice. And again, really the only way to do this is quadratic formula, which unfortunately you might have to do on occasion. But one thing that could happen to us like the last time is that we might get a critical value or both that are outside of the range of 0 to 24, then we can eliminate them. So take your derivative function, negative 017, 502 t squared, that's A, plus 385t, supposed to be a 2 right here, squared, and then minus 1.074. This is C and this is B. So t equals the opposite of B, plus and minus square root B squared, point, there should be a point here, minus 4 times A times C all over 2 times A. So 2 times 0.017502 will be negative. The bottom's going to be negative 0.035.004. And we got a negative out here. So this part right here, if you have a graphing calculator, you can do that all at once. So I can do that real quickly here and hit square root. Now a parenthesis already pops up because you might want to do more than one thing, literally like I want to do here. So I'm going to put another parenthesis for the 0.385, close that parenthesis and square it, minus 4, parenthesis negative 0.017502, and then another parenthesis negative 1.074, and then I close the parenthesis for that, and I'm going to close the parenthesis for the whole radical. So by typing it in like this, then I get that whole value. So we right now have negative 0.385, negative 0.385. The bottom is negative 0.35004, and plus or minus this decimal right here, 2702524894. So I just have to do one of these with a plus and one with a minus, and I can even do that here if you want. So be able to see this. So I'll put in 0.385, and then this calculator has a plus or minus button at the bottom, plus 0.2702524894, and then divide by the 0.350 0.5004 negative in the bottom. So the first possible answer is 3.278. Maybe they'll have me round that to 3.3. And that is between 0 and 24, so that's going to be a possible answer right there. And then if I do another version, minus 0.385 and put a negative on that, minus 0.2702524894 divided by 0.035004 negative, 18.719, which may be 18.7. And that's between 0 and 24. So this time both of them worked. So we could end up getting a local max and a local min here because of that. And okay, so now the only thing, see these problems, they're done the same way, they're just messier with decimals. Do they want nearest tenth? Let me check that. Oh, nope, it says nearest hundredth this time. Okay, so now we got to use 3.28 and 18.72. There's your number line. So I would plug in, is 0 exact? Yep, exactly 0 is included. So I would plug in 0, and I'd probably plug in 4 and 19 into the derivative function right here. And with a graphing calculator, that's not bad. Negative 0.017502. I'm not going to do the 0 first because that's easy. 4 squared plus 385 times 4 and minus 1.074. So I plugged in 4 into the derivative function and I got a positive. I don't care about the value, just the positive. So the derivative is positive anywhere on between these two critical numbers. So that's an increasing portion of the graph. The middle of the graph's increasing. The 0 part is negative for sure because there's a negative right there. P prime of 0, the t's would all disappear and it's negative. So the graph is decreasing first until I get to 3.28, then it's flat, and then it increases after that. So that's the first derivative test. You need a decreasing followed by an increasing at a critical number, and that's going to make it a local minimum. There's a local minimum at 3.28, and hopefully they don't want me to find the of, because that'll be messy too. But now I can reuse the fact that the middle is increasing. The middle's increasing. Is it going to then decrease on the other side of that 18.72? So let's plug 19 into the function. And if I press second enter, I can type over the 4 with a 19 by hitting 1. And then if you hit second delete, that lets you insert. So I can insert a 9 and scooch everything over. Get on top of the 4 and type a 1 from the 19, and then second delete is insert for a 9. That way I get 19s in there instead of 4s. And yep, it's negative on the other side of that critical number. So we went negative, positive, negative for the derivatives. That means we went decreasing, increasing, decreasing for the original function. So it's going to increase till it gets to this critical number, then it decreases after that. That's a local maximum. There's a local minimum at 3.28. There's a local maximum at 18.72. And it looks like they want the values too. So local maximum is at 18.72. The relative or local minimum is at 3.28. So I just got to get the minimum and maximum values by plugging these two decimals back into the original problem. So again, kind of messy here, but negative 0.005834 times 3.28 to the third power plus 0.1925 times 3.28 squared minus 1.074 times 3.28, and finally plus 18.68. So this is really messy without a good calculator. And I guess they want these rounded to the 100th as well. Okay, so 17.02, that's what I got for the minimum, 17.02. That's when I plugged in 3.28. So this is a polynomial. This answer is the maximum. This answer better be bigger than 17. It's impossible for this to, that's where I was messing up on that other problem. But here I can quickly hit second enter. I need to change all these 3.28s to 18.72s. So I'm going to put 18.7 until I run out of space, and then insert the 2. Get right on top of the 3. 18.7, insert a 2. 18.7, insert a 2. So yeah, good, that's bigger, 27.76. In a polynomial, the relative maximum value has to be bigger than the relative minimum value, because the graph can't break apart and do something else somewhere else. Okay, so was I anywhere close, or is it some other kind of mistake? Oh, wait. Okay, so my answers were right, but they wanted more answers than that. Did I not fill all the answers in? That's weird. I missed. Correct answer. 2 of them? That's weird. And then, oh, 0, okay. This is weird. I got all the answers, but there's extra answers in here somehow. Oh, I think I know why. 0 and 24. Because we have an interval from 0 to 24, you can get the endpoints of the intervals to be counting as well. That's what's going on here. So the 0 is here. I had 18.72, but 0 is another one. And then I had 3.28, but they have 24. So the extra 2 numbers are coming from the beginning and the end of the interval. And then, so that's why there's second values here as well. So what's going on here is when you have a polynomial like this, where was the original problem? I never wrote it down. The original problem is a negative t to the 3rd. So the way that looks is it's a graph that's going to come like this. So normally this is your local minimum, this is your local maximum. So remember, I got a minimum. The minimum happened first. Where did I put that? There it is, 3.28. The minimum happens first at 3.28. The maximum happens second at 18.72. What was it, 18.72. But the graph starts at exactly 0 and ends at 24. So even though these are not critical numbers, we're gonna do this later actually, where you also have to check the endpoints, although we didn't have to do this on that other problem, which is strange. But the endpoints can also be maxes or mins, just because the graph has a hard stop and start at those points. So because the graph is decreasing here, this can be considered a local minimum, and although it's kind of decreasing here too, but if you go in this way, see how that's a higher point there? So because it cuts off here, it's like it potentially could have been increasing and then decreasing after that, but you don't count this part, so it's just starting at a high point. So they're counting 0 as an extra maximum and 24 as an extra minimum because of that. So just make a note when you do number 15, once you get your 1 answers, you have to put the 0 is going to go in one of these and the 24 is going to go in the other one. And if you use your knowledge of the graph, of what the t to the 3rd looks like, The 0 is going to be an extra maximum, and the 24 is going to be an extra minimum. Okay, so we're almost an hour and 45 minutes in here, but at least you got a good basis for sections 5.1 and 5.2.